Okay, well, that was an interesting way to start the lecture. I'm sure the distance learning people who watched it are going to enjoy it. So tonight we're going to talk about fractured wells, and I realized that I did not include some material in here that I'll probably do for next year, but I'm really excited about this. This is one of those solutions where we did have some work done on this back in the late 60s, early 70s. It was kind of interesting. Actually, one of the first numerical solutions for fractured wells was generated by Dick Morris, Doug Von Gotten here in this department. It's a long story as to why they did it. I'm not really sure why, but then Gringarten, Ramey, and Raghavan came along in 1974, and they did some analytical work on this. And we'll talk a lot about that towards the end of the class. The first part of the class is miserable because it's math. The second part of the class is kind of interesting because it's about how we're going to use it. And at the end of the lecture, you're going to say, this is an awful lot of work for what? And then, you're going to realize, hey, nowadays we don't just have one fracture, we have hundreds of fractures, and they're all in a line, and we have to figure out how to incorporate that together. Now, you can imagine that these fractures are all going to be interfering with each other, and that's a completely different story. But for tonight, we're talking about the classic case of one vertical fracture. It is a vertical fracture in our case. I guess the orientation really doesn't matter, but for the sake of sort of argument and thought process, it is vertical. There were some concepts when Gringarten was working on this that anything shallower than 2,000 feet is a horizontal fracture, anything deeper than 2,000 feet is a vertical fracture. Right now, of course, we assume that most fractures are vertical. Why? Because the maximum principal stress is going to be on top of it, and you're not going to lift the earth with a fracture. However, some of the recent tests where people have gone in and drilled a core through fractures, and even there were some mine back tests done in Colorado in the 70s back when we were pouring money into this problem. They actually went down and mined out. They put a well in, put a hydraulic fracture in, and then mined it back. And you'll notice the fracture bends and twists. Obviously, it has to because of the nature of the local stress heterogeneities. And there was sand in some parts of it and sand not in others. And, even now, whenever you're hydraulically fracture stimulating well A over in well B, it starts producing sand because you're literally injecting it thousands of feet away and it's going into that other well. But for the sake of argument tonight, again, all we're talking about is a single vertical fracture. It could be created just with water. This is called a slick water fracture treatment. They put chemicals in it, obviously, to reduce viscosity and so you don't react with the formation and that sort of thing. But it's a lot cheaper to just pump water. It's also, I want to say this in a way that I don't get people sending me angry emails, but there was a time about 20 years ago when the service companies decided that they would pump only slick water treatments and no proppant, and that would be an effective means of stimulating a well. It turns out that wasn't particularly effective, although there's some evidence to suggest that you could repeatedly fracture something with slick water and it might help. But think about it. You have to have something to prop this open. Now, we're not going to talk a lot about this tonight, but there's two basic theories. How does rock fracture? It either cracks open like this or it shifts like that. So there's either shear fracturing or, I forgot the name of it, but whatever, splitting open like that. If it's shear, then people think that there's a displacement so that the fracture essentially remains. If it, and my brain's not thinking very well tonight, but if it fractures this way, then it'll reseal whenever you let the pressure off. That's, of course, why you put proppant in. And proppant has all sorts of problems, right? It's what's the cheapest thing to pump? Sand. Well, there's cheaper things than sand, but sort of the cheaper-ish thing to pump is sand. What were they pumping at first? Does anyone know? Sorry? Mm-mm. Sorry? No. What was the first proppant that was used? Sorry? Walnut shells, yeah. They were pumping nut shells down. So it's really strange when you think about it. I guess you could pump pistachio nuts down. If you guys eaten pistachio nuts, yeah, and you know how sometimes there's one that's unopened. Do you know what they say about that particular pistachio in Iran? No? It's either the nut or the tooth. Fate decides. So if you get one that's not open, I'd probably not try to break it with your tooth because you may lose. Getting back to fractures. Mathematically, this is not fun, but it's not that bad. So like I said last night, we're going to take a single line, we're going to integrate it across another line, and that creates a plane. That'll be our fracture solution. Is that enough? What do you think? Probably not. In order for us to actually model fracture, it'll have to have width, right? Okay, so let me ask you guys a real quick question. How big, what's the maximum width of a hydraulic fracture in your mind? And let's ask the math ladies first. So we're pumping water in the ground at extremely high pressure, and it fractures a rock. How big do you think at the well bore, because that's where it'll be a maximum, how big do you think the fracture is? Is it like this big, this big, this big? Less than 1 meter. Yes, thank you. Anyone else? Centimeter, approximately. That'd be about the maximum you're ever going to see. It's about a centimeter. And then as you propagate out, it's usually maybe 2/10 of a centimeter, maybe 1/10 of a centimeter as it propagates out. I mean, this rock is under extreme stress, and you're injecting fluid in. Have any of you ever been in a mine and seen fractures that have refilled with calcite or with quartz or other materials? These fractures are not particularly big, and the rock fractured for God only knows what reason, and then things came along and refilled the fracture. Sometimes they'll be maybe 2/10 of a centimeter or 1/10 of a centimeter, but we're going to artificially fracture this rock. Where do you think the fracture goes? Like everything else in life, right? The path of least resistance. The rock itself has a tremendous amount of integrity, but if there's a pre-existing fracture, what's going to happen? It's going to go down the pre-existing fracture. But almost all pre-existing fractures are full of what? Cement or some other mineral. And if that mineral's tough enough, it's not going to fracture. So that's another question. How many of you are familiar with the Haynesville Shale? Yeah, a little bit. Okay, so the Haynesville Shale actually has a geological phenomenon where there was in the ocean at the time, there was a microscopic organism that would bloom and it would die. It would bloom and it would die. And it would bloom and it would die. And they had these microscopic skeletal fragments, and they would drop to the bottom of the ocean. Remember, shales are in the most quiet part, right? Most quiet part. So there's nothing going on. And over time, these little layers of these skeletons would form. So the shale has a lot of integrity, but these little layers don't. So if you look up on Google right now, core for the Haynesville Shale, you'll see it's all coming out like in poker chips. Like when you play poker, the chips you use. Why? Because it hits that, the drill bit hits that, and it splits that plane apart and the rock breaks. Okay, it's very hard to get a high integrity sample out of the high pressure part of the Haynesville. The other thing is it's under extreme overpressure, sometimes as much as 1.1 psi per foot. The normal gradient is 0.465 psi per foot, so almost, well, it's more than twice the normal gradient. So it's a lot of pressure. And you have to inject at a very high pressure in order to fracture the rock. So there's actually a concept that in the Haynesville, you're not only getting vertical fractures, but it's a possibility that you're also getting horizontal fractures. What do you think of that? Hadn't thought about that before. We really hadn't had a case to discuss that. But that would mean that our fracture would have to have like planes going off of it as well. They probably don't go very far, but it could happen. I have another student who did a dissertation on this, And not only from fracture theory, not only is there a primary fracture that extends, hundreds of meters in that direction, but there's also a secondary fracture that can extend a few meters. It has to do with the stress planes. So there's all sorts of complications here. I'm telling you all this. I'm taking up your valuable time. Why? Because I want you to understand that the concept of a perfectly planar vertical fracture is a fantasy. Okay? If we want to have conductivity in that fracture, we're going to have to put something in it, more than likely. Now, when I was your age, Schlumberger was really into acid fracturing. Why? It's just as easy to pump acid as it is water. Okay, so they were pumping a lot of acid. They called it a whisper frac or something like that. And what they would do is they would pump it in a carbonate formation, and they thought that it would differentially eat the rock, so it would actually leave pieces of rock that would hold it open. Who knows? It may, this is what service companies do, and some of you are going to go to work for service companies, so I probably need to zip it. But, Schlumberger came out with a concept called a highway frac. Baker Hughes has come out with something else. There's a concept of using lighter than water proppant, so it'll carry farther. But if something floats, it's probably not very strong. How big do you think the material is that we inject into a fracture? How big is the sand? Is it normal beach sand? Any ideas? That would be one probably average size. Okay, probably beach sand would be average or a little bit larger than average. Okay. So what size are they pumping now in most of these jobs? Does anybody know? 100 mesh. And 100 mesh looks like baby powder. Okay. Right. So it's dust, essentially. Why 100 mesh? Because you're not creating a very big fracture, for one thing. And you want this stuff to travel as far as it can. There's actually people pumping 200 mesh, and now there's a synthetic 300 mesh that someone wants to pump. Okay. It's more like a powder, like a fine powder, than a sand. No, it would be smaller than a millimeter. It would, like baby powder, it would be on the order of that. I don't have a convenient measuring scale. But if you thought about it, if you were to have a couple of layers of that material relative to a shale that's maybe 10 times 10 to the minus 6 millidarcies, that's still an enormous amount of conductivity. Okay? Just, again, speaking out loud. But traditionally, people sold hydraulic fracturing on conductivity. So Cam, let's say you become a hydraulic fracturing salesman, okay? And 100 as a number is essentially infinite. 10 is sort of intermediate, 1 is low. If you design for 100, you'll probably deliver 10. So if you design for 10, you'll probably deliver 1. And the stimulation companies hate when we say this, but this is probably true. So you're going to have to decide how you want to design your stimulation treatment in order to deliver conductivity. And also, of course, they have all these clauses in their contracts which say, they'll do the best they can, but no promises. So tonight, what we're going to talk about is a perfectly rectangular fracture which has uniform flux. So if I'm looking at this screen, all points on the screen, the flux coming into it is uniform. Is that okay? Sure, why not? Okay. And then if this fracture had width and it had permeability, that would be a so-called finite conductivity fracture. And that is a much more difficult problem, as we talked about last night. Okay, so in 1974, Gringart and Ramey and Raghavan proposed this solution. And this looks god-awful, right? How many people say it looks god-awful? Everybody, right? Okay, so the first thing we'll do is we'll say that the exponential integral arguments are valid. So TD is large. Okay, TD is large. What happens when TD is large? Well, what is ERF whenever TD is large, class? So you have TD in the denominator. The argument is going to go to 0, right? What is ERF of 0, class? 0. So 0 plus 0 multiplied by anything is? Very good. And then you're left with what? A couple of exponential integrals added together, which looks a lot like radial flow, which is exactly what it is. On the other hand, at small times, when this particular solution has a small time, what is the value of the exponential integral for very large arguments? It's 0. So 0 plus 0 is 0. What about ERF? Well, for a small argument, what is that going to be? That's going to yield a large, for a small TD, that's going to yield a very large argument for ERF. For greater than about 3, ERF is equal to what? 1. 1 plus 1 is what, Mr. Ravi Kumar?
2.
Multiplied by a half. So the solution is square root of time. Okay? Does everybody get this? So this solution not only matches the early time behavior, which is dominated by linear flow, and linear flow is whenever the fracture does not know that the tip exists. Okay? That means that the flux coming into the fracture is uniform at all points and there's no tip effect. What's tip effect mean? Well, it means that there will be a curl around the end. Okay? So when the tip effect becomes noticeable, this solution goes from being linear to sort of being like a cigar, and then eventually it becomes an oval or an ellipse, and then it becomes radial, that distribution of pressure. And we'll talk a lot about this. But that solution, at least conceptually, models everything. Now, nobody really asked about the XD, but that's okay. You can imagine that XD is probably 0 for the wellbore, but we'll talk about that in a minute. Okay, so for XD equals 0, we have the uniform flux case, and for XD equals 0.732, what do we have? We have a correlation that Gringart and Ramey and Raghavan sat out and they said, we need to figure out how to make that solution. Okay, let me rephrase this. Ready? This solution is a uniform flux solution. Can a uniform flux solution act like an infinite conductivity solution? And again, an infinite conductivity solution is where a particle of fluid enters the fracture tip and goes to the wellbore with no pressure drop. How would you make that happen? Sorry? That's a good idea, actually. Well, it turns out there's a magic point along the fracture that behaves like an infinite conductivity fracture. And they figured this out. And that magic point, and this has been done by Gringart and Ramey Raghavan, it's been proven by Kuchuk, it's been proven by simulation. That magic point is 0.732. Okay? So if you evaluate the uniform flux solution at 0.732, with that being 0, this being 1, somewhere in here, then you achieve essentially the infinite conductivity vertically fractured well solution. Okay? It's a trick, but it works. Okay? So we have uniform flux or infinite conductivity, either one. Okay? Now, as I mentioned a moment ago, and Mr. Ravi Kumar helped me with this, if the time is very small, argument is infinity, infinity, that's 1 plus 1, 2, so this is the solution. Of course, these two are 0 at that point. And then the long time approximation, these arguments are 0, so that's 1 plus 1, or sorry, 0 plus 0 multiplied by that, and then we get these. So for the uniform flux case, you have that, and for the infinite conductivity case, you have that. And this is less than 1% error for TDXF, which is the dimensionless time on fracture half length greater than 10. Okay. Next is what we're going to derive tonight. And I know you're looking at this going, God help me, but this isn't nearly as bad as it looks. And the only one we're really interested in is this one. So it turns out that this solution in the Laplace domain is going to equal this solution in the real domain. I can't prove it to you right now, but I can tell you it's going to happen. So Cam, how would you prove this? if you were on a desert island and all you had was a stay-fast algorithm and Microsoft Excel, how would you prove this? Well, you take the solution on the previous page, calculate it in Excel. You take the solution, this first one, and calculate it with the stay-fast algorithm in Excel, and they better come out to be the same, okay? But otherwise, how would you prove it, class? How would you prove that these two are the same? Sorry? You would invert the solution. That's not possible, but it is possible to take the kernel, that is the KERNEL, the starting point of this solution, and show that it's equal to the solution on the previous page. Therefore, when you take the Laplace transform of that, this is the result. So I hope you understand what I'm saying, but what we're going to derive tonight is this thing, not the same thing that Gringarten, Ramey, and Raghavan did, but it's the same thing that Jose, Horn, and Ramey did. Notice Ramey is in both of these. So this solution that we're looking at tonight on this page is actually not part of the other solution that Gringarten, Ramey, and Raghavan did. They're independent. But your intuition is correct. If you could invert this, then you could take it and compare the two, but that isn't how it's going to work. What we're going to do instead is we're going to take the thing that we started with here and show that it equals the Gringarten, Ramey, and Raghavan solution. Okay? Mathematically, not numerically, mathematically. Okay, I'll have to show you that on the next page. Just be patient. Okay. Now, what happens is, because we were able to use the line source solution to derive the infinite acting case, we can also use the line source solution to derive the finite acting case. And I don't think it's any surprise that our good friends, the Bessel functions K1 and I1, K0, I0 are here, and then the integral of I0 is here. So just like last night, this is the part where we're integrating over distance. How many of you want to devote your life to something unique? Anybody here? Like, preservation of teddy bears, or, some sort of eating more of some type of candy bar than anybody else. Does anybody have some sort of desire to do something? I mean, does anyone here have a talent where they can do something that's so unusual that they should live their life doing that rather than being a petroleum engineer? I mean, I've had concert pianists, I've had welders, I've had apparently struggling comedians take this class. I've had pretty much everything. But is there somebody in here who wants to devote their life to something truly, what's the right word I'm thinking of here? Trivial? Okay. So there is a gentleman named Udell Luke, and he devoted his life to the integral of Bessel functions. He wrote a book on it, and there's a copy of it in your references. He basically spent his adult life coming up with relationships for the integrals of Bessel functions. Now, looking back, that was notable. Of course, now you don't have to do that because you have Mathematica and other tools like that. But for us, when we saw that, when I was your age, it was like, what are we going to do with this? Because how do you calculate the integral of K0? Math ladies? No comprende? Okay, there is a direct solution for the integral of K0. It's a triple loop. Okay? So there's 3 nested infinite series. So they all have to converge. Mr. Desai is smiling because he knows that you're going to have to go to some super precision to get them all to converge, and probably you're going to make a mistake, but you could map it out. At any rate, what I'm trying to get at is, did we jump out of the frying pan and into the fire by going from something that's relatively well known, like the exponential integral, to now the integral of the Bessel function K0? Well, it doesn't matter. We'll cross that bridge when we come to it. Okay. Did Alex talk about how computers think? No? Computers can only do 5 operations, right? Add, subtract, multiply, divide. So somehow we're going to have an equation for K0. We'll come back to that, or I0, or whatever. So again, this is the Ozcan-Raghavan solution, and this is the Gringarten-Ramey-Raghavan solution, and their comparative here. Now, how many of you guys remember the story of the guillotine and the convicts? You guys remember the story? I told you this, right? So there were 3 convicts who were supposed to be killed with the guillotine. And the rule is if the guillotine stops or fails or whatever, you get to go free. So the first one is crying and screaming and hollering, and they drop the guillotine and it stops. It's like, oh, it's a miracle, I get to go. And the second guy, he's crying and screaming, and they go to the guillotine, drop the guillotine, it stops. Okay. So the next guy is an engineer. What does the engineer do? Sorry? No. He goes, I think I see the problem. Okay. So Ozcan and Raghavan looked at the Jose, Horn, and Ramey solution, and they said, we think we see the problem. Jose, Horn, and Ramey left the integral that we were talking about a moment ago in a much less enjoyable form. In fact, it had to be integrated numerically. They even talk about how they had to break up the solution into segments in order to integrate it. And, I can't speak for, Dr. Raghavan helped me make my career. I worked with him for about 3 years, and Dr. Ozcan is probably my closest friend in petroleum engineering, so I can't speak negatively of them in any way, shape, or form. But they saw that the the Jose, Horn, and Ramey solution had a reduction, and tonight we'll do that reduction. And when we're done, you'll go, well, this was really easy. And I don't know why Jose, Horn, and Ramey didn't see it. But it's kind of like the Gaver algorithm and the Stayfest algorithm. These guys get a bit more credit for coming up with a much easier final form than Jose, Horn, and Ramey. By the way, Jose is whom? Yes, he's the managing director of CAPA. This is where he started his career, obviously, in well testing. So the first thing we're going to do is look at the continuous line source solution. And we're going to start with Carcel and Jaeger. And I have to admit, the reason we do this is just to drive you insane. But we're just showing how they would use Kelvin's solution to derive the exponential integral. Those of you who are paying attention, you just jump to the bottom and there's the answer. But it's important that we recognize we're using the continuous line source solution. We're going to integrate that solution over time. It's a convolution. And when we do that, we have to make some substitutions. The definition of the rate is given here. The definition of eta is given here. We just keep working our way through it. We're going to have to non-dimensionalize it. We'll have to use a variable substitution, et cetera, et cetera. But now when we get to the bottom, and I'll just jump to it, this is the same thing we derived last night. So this is the continuous line source solution. We derived it last night using Laplace transform. We derived it the night before last using the Boltzmann transform. It may seem trivial to do this, but I wanted you to understand this is our starting point. So this is a pressure drop due to a continuous line source solution. And again, it's exactly the same as what we did 2 nights ago, or last night and the night before. So now what we're going to do is we're going to integrate it across a line, and we're going to create a plane. So in this case, it becomes the pressure drop in the fracture, and we have to define the rate in the fracture, which is slightly different because it references a different reference length. The reference length, or the characteristic length, is now 2xf because we assume 2 equal length components. We're integrating from xw to xf and from xw to minus xf, which makes sense. And then, of course, we're integrating that line source solution that we just talked about. So we're taking this solution and essentially substituting it into an integral across that line. And then we make our definitions, we make our dimensionless variables, etc. And we continue to work our way down. This is a lot of ugly algebra. You have to divide everything by xf. You have to work through deciding how you want to define your dimensionless variables or your variable substitution. So you're going to have to define an XWD prime, you're going to have to define the derivative, and then you pop up on the other page, and where we finally end up is with this. So this is our quasi-dimensionless form of the fracture solution. So this is the starting point of where we're going to go tonight. Okay, this is the starting point. So all of that algebra before was to get to this point where we have a planar source now, and it's equal to 1/4 the integral xwd minus 1 xwd plus 1, and you can imagine in a minute we're going to say that xwd is 0, e1 xd minus xwd prime, which is a dummy variable integration, yd minus ywd prime 4 over td. All this looks familiar. If we were smart, we'd start eliminating things. So xwd is going to be 0. We're going to assume symmetry, and then we're just going to get rid of the yd because we're not going to look at a pressure distribution. We're just going to look at the pressure at the wellbore. So we're eliminating xd and yd by saying we're going to solve at the wellbore, which is where xd is, and we're going to solve at the wellbore, which is where, okay, so xd and yd are 0. And when we do that, this whole thing reduces to this. Okay? What does that mean? XWD, pardon me. This is our starting point. So now we have 1/4 integral minus 1 to plus 1 e1 xd minus xwd prime, which is just dummy variable integration, that quantity squared, over 4td, and then the dummy variable, the differential of the dummy variable. Now, how do we take the Laplace transform of that? And by the way, that is our starting point. If we can successfully integrate equation 19, then we can obtain the Gringarten-Ramey and Raghavan solution. Okay? If we can successfully integrate equation 19, then that's what we'll get. And by the way, that is not part of this discussion. That is an exam assignment from several years back, including last year. You go from equation 19 to the Gringarten-Ramey Raghavan solution. That's not what we're doing tonight. Okay? What are we going to do tonight? We're going to assume that that's valid, and we're going to continue. So we're going to take the Laplace transform of equation 19. How do you take the Laplace transform of an integral? Think very carefully before you speak. This is an integral with respect to space, not time. If it were an integral with respect to time, what would happen, class? We would end up with a 1 over u f of u. But this is not what's going to happen. This is going to be the integral of f of u with respect to the spatial variable. So we can simply perform the Laplace transform operation, but everything else comes out, and the Laplace transform actually goes in. So we're actually going to integrate the Laplace transform solution is the integration of the Laplace transform of the E1. What is the Laplace transform of the E1 function, class? It is 1 over u k0 square root of u times a, right? It's that simple. We're almost done. So then we work through a bit of algebra, and this is the final form. And this is exactly, precisely what Jose, Horn, and Ramey proposed in 1988. It was that simple. Why did they do all this? Because they needed a solution in the Laplace domain. What is another approach you could have used to get the solution in the Laplace domain, class? Again, Alex probably didn't talk to you about it, but it was one of the reasons that I derived all of those different relationships for taking data into the Laplace domain. This is a monotonically increasing function, correct? And, well, even if it wasn't monotonic, it doesn't oscillate. It's relatively easy to take the Laplace transform of a function like that when it's defined by data, and that's actually how I first proposed it. I used the Gringarten-Ramey Raghavan solution, discretized it, and took the Laplace transform by using values of it. But Jose, Horn, and Ramey came along, and their equation 22, or my equation 22, their whatever equation number it is, that does the same thing. That is the Laplace transform of the fractured well solution. Now the problem is that the integral you now have an argument inside of here. And when you have an argument inside of here, you're going to have to either do a trick or you're going to have to discretize it. And like I said, this is a starting point. So Ozcan and Raghavan come along and they look at this and they say, okay, that's an integral that is minus a to plus a, some function b multiplied by the quantity c minus z, and then the differential dz. So a good variable substitution would be x, and x is going to be what's on the inside. All right, so x is b multiplied by c minus z, and then you define at z equals a. You have this function at z equals minus a. You have that function, no problem. You have to define your differentials. Dx is minus b dz. Dz is minus 1 over b dx. And we're going to start doing some things with this. Now, when we do that, we simply rewrite the integral as this. Okay, that's no big deal. And then we're going to have to reverse the limits to straighten out the minus sign. So there's that. And then we start playing around with it. We're going to need to expand this. We're going to need to break the integral into two pieces. Why? Because we want the integral, when we go from a to c and from c to b, it's actually a to 0 and 0 to b. But we're going to reverse the limits of this term and just continue to work through the calculus. So as we continue, we have this. If we look at the first integral, we're going to have to operate on that. So we're going ahead and define a variable of substitution. And what happens is, if it's an even function, that is, if f of x is equal to f minus x, then we can simply reverse I1. And by doing that, we end up with the complete integral looking like this. Now we're almost done, because what is f of x? F of x is k0. And what are all the other terms? Well, they're already defined. So the complete integral looks like this. And then we just substitute a is equal to 1, b is equal to square root of u, c is equal to xd. And this is our almost final form. And then this is our final form. So we successfully changed the form of that integral from equation 22, which is not directly, you can't evaluate it directly, into equation 33, which you can evaluate directly, assuming that you know the integral of k0. Okay? And again, as I mentioned before, the integral of k0 is a triple infinite series summation, which is really ugly. At the limiting value of infinity, it's pi over 2, which doesn't really help, if you want to know the truth. I had to go to quadruple precision Fortran to calculate this in 1988 and 89, so this was really not fun. Okay, and then someone pointed out to me that there was a book on integrals of Bessel functions, so we'll talk about that. These were the other solutions that we derived last night. So we come over and we take a look at how do we calculate these integrals, and it turns out that there is a book of integrals of Bessel functions, and that book is given by this gentleman, and it just so happens that here's the integral of k0 and the integral of I0 and so forth, and they've been given approximations that are essentially single precision, but they're probably accurate enough to use for what we want. And of course, now that we have Mathematica, it's irrelevant. You can evaluate the integral to whatever accuracy you want. But at the time, we were using these expressions to calculate the integrals of k0 and I0. And so there's a few more of those. Now, I'm sure there are no real questions about that. You obviously will have to rederive it. Yes, sir?
So essentially, the solution that you showed us, the solution in real space, can be obtained by integrating
Equation 14, is it? I did not require this year, and I've been reluctant to give the solution to this. Sorry, it's not 14. It's 21. Or sorry, 19. Thank you.
So
You can carry out the calculus using equation 19 and end up with exactly Gringart and Ramey Raghavan's solution.
So what was the motivation behind? I apologize
Sure.
if I missed it. What was the motivation behind taking it to Laplace?
because we wanted a Laplace transform solution. At this point, the software will require a Laplace transform solution. Remember that the software is going to have wellbore storage in it. The solution is going to have wellbore storage in it. We haven't derived this yet. I mean, I'm saving that for last. But we have to have the Laplace transform in order to use wellbore storage. There's other things as well, and we'll talk about that tomorrow night, which is the naturally fractured reservoir solution. The naturally fractured reservoir solution and the wellbore storage solution both require Laplace transform variable. There's also Laplace transform solution. There's also other things that do as well. So at this point, everything was converging to needing a Laplace transform function. Now, Mr. Ravi Kumar probably doesn't remember this because he wasn't born yet, but there was a product called Pan System. And Pan System used sort of an integration technique to integrate wellbore storage in. It's a recursive technique to integrate wellbore storage into their solutions. Now, it would not work for naturally fractured solutions. You're still going to have to go to Laplace transform for that. But back when this product was first introduced, this was actually a technique that Cinco and Samaniego introduced whenever they did their wellbore storage solution for a finite conductivity vertical fracture, which doesn't mean anything. It just was, they showed how to derive a recursive technique to add wellbore storage to the solution. It's unstable, though. Remember, recursion is unstable. So, you know, that is what Pan System did. And so they did not bother with Laplace transform solutions for certain things. You know, their software had a workaround for it. But you, at that point, you could not use the fractured well solution with the naturally fractured reservoir condition. A little bit later than this, Thompson et al. From Tulsa, again, some cronies of Ragavan and Reynolds, showed a general formulation for how to bring Laplace, using the Laplace transform solution, how to bring naturally fractured reservoir characteristics into the homogeneous solution. And we'll talk about that tomorrow night as well. So the big answer to your question is we didn't need to do this per se, but we wanted to do it so that we would have a relationship that we could always combine with wellbore storage and with naturally fractured reservoir effects. You can also do superposition. I didn't mention that, but you know, that's more or less kind of obvious, I guess. Again, we haven't talked about superposition, so my apologies. Okay, so we came along, and our good friend Cinco and Samaniego proposed the finite conductivity vertically fractured well solution. The very first regime is what? The fracture is its own reservoir. The fracture is its own reservoir. So that's what you're looking at, fractured linear flow. How fast will fractured linear flow occur, class? Sorry? Ken? Very fast or very slow? Extremely fast. Very high permeability fracture. Are we talking about on the order of seconds? Yes. What do we have at early times? We have wellbore storage distortion, right? We're never going to see fractured linear flow. I don't make a lot of absolute claims from this pulpit, but you're never going to see fractured linear flow. You cannot. If you have any tubing volume at all, any casing volume at all, you will never see fractured linear flow. Okay? So the next regime, if you have a low conductivity fracture and linear flow, you have bilinear flow. So that's certainly a possibility. You can also have formation linear flow, which is what we've been talking about with the uniform flux solutions and the infinite conductivity solutions. These will be early time-ish, within the order of minutes, that kind of thing. Okay. Now, everybody heard what I just said? Formation linear flow or bilinear flow, whichever one it is, should occur within minutes. Everybody agree? But then when you look at data from production of Marcellus wells or Haynesville wells or Eagleford wells, there's a period of maybe a month or two before you see linear flow. Whose fault is that? It's a trick question. Whose fault is that? How does a shale produce fluid? it has to produce into a wellbore, right? And how did you create that fracture system? Sorry? You injected a lot of water. When you first turn open a shale well, what do you usually produce? Water, 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 water. I was asked to look at a well about 5 years ago. It was a little more than that, 7 years ago. This is 2017. It produced water for 45 days before it produced hydrocarbon. The company chewed off all their fingernails and was, rolling around on the floor in a convulsive state. It was not an economic well. It was on the fringe of the play. But 45 days of producing water. And at that time, we were expecting to see maybe 2 weeks of water production or so. Now, in contrast, the Haynesville Shale, the second you open the well, however long it takes for fluid to travel from the bottom to the top, you can count maybe a few minutes, it's going to be gas, like a freight train. Now, it'll produce a lot of water as well, but like a freight train. How much water do most shale plays produce? If you inject 100 units, how much do you get back? 30 is a really good number. Good guess. As low as 15, probably not much higher than 30. That'd be the upper limit. When I was a kid growing up, there was a fried chicken commercial, and they would take a cup of oil, fry the chicken, and then pour the oil back in, and so you got almost all of it back. Same thing with this, except that it didn't work that way. This is more like unhealthy fried chicken. All the oil stays in the chicken. So is there anything you can do to improve that? What do you think? In the course of doing things for other people, you find really strange behavior. Like, Cam, where you're from, there's a part of the Marsalis that has a salt intrusion, and it's a really bad area. But almost the same day, the salinity of the water jumps to an astronomically high value. Ordinarily, the water penetrates a formation, and as you're producing it back, the salinity increases as it leaches the salt out. But this thing was just mega salt infested, and it would come back almost completely saturated, maybe within a day or two, maybe a couple of 3 days at the most. So again, this early behavior in the scenario that we're talking about here with conventional reservoirs, you're not going to see a lot of produced back fluids because the water is imbibed in the formation. It's leak off. Sometimes you will, sometimes you won't. But in terms of shale, you're going to have a very long period of where that fluid is produced back. Okay, just as a comment. And by very long, I mean it could be weeks or months. I also want to mention, just as a comment, I'll come back to you, Mr. Ravi Kumar, that I noticed something the other day that by using surface pressures, which are kind of corrupted by the production, you can't really see linear flow. So just FYI, if you're going to look at productivity index, you really need bottom hole pressures. Yes, Mr. Ravi Kumar.
So when you say you were producing water, producing water in formation heating.
That you injected, yes. But there's so much calamity going on that you don't really see the formation signature yet. Now, in some cases, when you open the choke, you will get to that period much faster. You'll produce that back pressure off. You'll produce that water load off, and you'll start to see the reservoir signature sooner. That is a positive of having a higher choke. What's a negative of having a higher choke, class? Remember all that sand you pumped in? It's coming back. Okay. Some companies have a strategy, just to hell with it, we'll produce the sand. Some companies don't want to produce the sand. Some companies have tried sand mitigation, etc. There's other issues as well. When you open a well up, what does it do to the stress in the formation, especially near the well? It's severe. So there were cases in the Haynesville where they went to this thing called set it and forget it choke. They just set the choke and they left it that way for years. My student who works for a consulting firm, did a whole bunch of these cases, and he found out that within reason, within a minor bit of discrepancy, it didn't really matter. Now, there are plays where choke management is absolutely critical, such as the Niobrara or the Codell Niobrara or the Eagleford, and to some degree some parts of the Delaware, where if you're not careful with your choke, you're going to bring gas on, and you're going to bring some problems. It's not a reversible process. So, okay, I'm doing a lot of talking about things that aren't relevant, but for tonight, we're going to talk about these particular flow regimes. We're going to see bilinear flow, we're going to see formation linear flow, and in the good old days when we were talking about 1 millidarcy formations, that was low permeability when I was your age, 1 millidarcy, you would see pseudoradial flow. It's possible that if you work in shales, you will never see pseudoradial flow in your life. Okay? Just FYI. I threw this in so that you'll understand what Cinco and Samaniego understood about this problem is that you had to look at the flux distributions in the fracture. And in particular, you can see these flux distributions, they generated, I'm trying to think of how to do this without losing my headphones here. They generated these flux distributions, and they're showing the infinite conductivity solution here, and they're showing their study, and you can see the infinite conductivity solution. I'm trying to pick the point where it intersects. I think it's here at 1. Yeah, let me draw a line, sorry. So at 1, where do these intersect, class? .732, correct. Okay. Now, you'll notice something a little strange, that out here at the tip is where you have the craziest flux. Over here at the wellbore, things are actually fairly well behaved. However, that changes when you start looking at flux distributions for different fracture conductivities. And these, apologies here, but they were using the symbol pi in their definition of conductivity, so sometimes it's kind of confusing. This one does actually have pi in it. It's W, which is the width of the fracture, multiplied by the permeability of the fracture, divided by the fracture half length and the formation permeability, but they included the symbol pi, the number pi, pardon me, because of the way they formulated the solution. We do not use pi anymore. We just use WKF over XFK. But look at the distributions of flux here and at the wellbore. So very, very different than you would expect. And the lower the conductivity, the more severe the flux distribution. The higher the conductivity, like I was saying before, the more it behaves like uniform flux or infinite conductivity. Just be aware of that. Now, how do you calculate the fluxes? Well, like they showed here in this diagram, you have to discretize the fracture. And Mr. Liu, how many cells do you think you're going to have to use? 90. And in modern computers, that's not very expensive, but we were running about 40 when we were doing this problem. Because if you went much higher than that, it got expensive computationally. Okay, just FYI. Next is the great debate. Okay. You know how you can never convince some people about some things? Pretend this is the 1970s. You're the pioneer. You came up with the idea of a finite conductivity vertically fractured well solution. And somebody else has another idea. Okay. There were people at the time that absolutely, positively did not believe that a finite conductivity vertically fractured well solution existed, that you could not create a fracture, fill it with proppant, and that had any physical relevance. They thought it was either infinite conductivity or uniform flux. And don't bother me with the facts. You guys understand what that means? So what they decided, the people that were in the opposition, if you want to call it that, is they decided that this was a skin. They decided there was no such thing as finite conductivity, that it was a skin. And fortunately, Cinco and Samaniego are pretty smart. So what they did is they produced some solutions, and just for the sake of argument, I'll draw it like this, and then I'll draw it like this. So that's the infinite conductivity and the finite conductivity solution. And then what did they do, class? They added skin. Well, if I could get this thing to behave. What's your favorite color, Ricardo? I already used blue. What's your favorite color, Ravi Kumar? Like money, right? I get it. Are we going to start calling you R money or G money? Okay. All right, so what they did is they added a skin factor. This is just a constant. So they said plus some number, and it causes this behavior. Is that finite conductivity, class? It's pretty simple. How do you get rid of this? Take the derivative. And that'll tell you immediately that this is wrong. This concept is wrong. It is not a choked fracture. It could be a damaged fracture. I'll give them that. Because later on, after all this happened, people began to say that there could be a fracture face skin. So depending on whoever's model you look at, there's company I and there's company K. And company I, they like to use sort of a radial flow skin. And company K, they've been using fracture face skin probably for 20 years, maybe more. So there is a possibility that there could be some, you know, what they're calling fluid loss damage or fracture face skin type phenomena. But for the sake of argument, the finite conductivity solution is definitely independent and valid. It is not simply adding a skin to the infinite conductivity or the uniform flux. We already talked about this, and now very quickly we'll talk about this. What about the end of bilinear flow? So you'll notice that I've marked all of these cases, and this is the original plot from Cinco and Samaniego, and you'll notice that I put a line. So this is a quarter slope line here, it's a half slope line here, and this is the end of bilinear flow for each one of these cases. And there's kind of an oddball feature that there's something that happens over here, but that's okay. And then there's an end of linear flow feature over here. I use donuts just so you can remember it, okay? So what does the end of bilinear flow mean? What's happening with the end of bilinear flow? So you have flux down the fracture and you have flux coming into the fracture. So again, it's the tip effect. When the fluid begins to, the pressure distribution begins to curl around the outside of the tip, that's the tip effect for, that is the end of bilinear flow. The same thing is true for the end of linear flow, and you can see that all these cases down here are essentially linear flow, or sorry, they're essentially infinite conductivity, and they provide a linear flow solution. So, you know, somewhere around here, I think we used to say it was 0.01, or sorry, 0.02 was the end of linear flow, and there's a huge transition before radial flow, but that would mark the end of linear flow. And that, of course, is also where the tip effect occurs. So, any questions about that? Probably not, I guess. Okay. This is the famous plot by Cinco and Samaniego, and I want to be honest, whenever you're sitting here looking at this, you're probably all going, what the hell is this? So on the y-axis, it's RW, the wellbore radius, e to the minus s, and this is the radial flow skin factor, not the fracture face skin, divided by xf, plotted against fracture conductivity, dimensionless fracture conductivity. So what does it tell you? For a fracture conductivity greater than 10, you have essentially a constant behavior. Okay? So this is actually what was used to calculate an equivalent radial flow skin factor. So if you know the conductivity, you know the fracture half length, let's say from a well test, then you could calculate the skin factor. Why is that important? How many of you like when your grandparents tell you how the good old days, Coca-Cola was a nickel and forget it. Okay. When fractured well testing became a part of the landscape, people would go to their manager and they'd say, the fracture half length is X, and the conductivity is Y. And what would the manager say? I don't know what that means. You'd say, I need to know a skin factor. Tell me the skin factor. So this is a calculation of skin factor so that you can explain it to your manager. Okay. Why would they care what the skin factor is? Because that's what they understood. They understood from the radial flow system that this was an equivalent, that this was, if you had a positive skin, what did you want to do? You want to stimulate it. But this is already stimulated. So most of these skins are going to be negative, and some of these are going to be extremely negative, just so you know. What's the maximum negative radial flow skin factor that you've ever heard of? -1, -2. Naturally fractured reservoirs, -3. This will be -7. Okay. It's physically inconsistent as well. It's not, you cannot have a -7 skin factor for a radial flow system. The wellbore would have to be as big as this room in order for that to happen. All right, I think I'll stop. Yeah, I'll stop now. Okay. So you will be required to rederive that. I'm sure you'll love it. It's all there. No problem. How would you go about creating a multi-fractured horizontal well solution? Anybody? How would you do it? So geometrically, we took a line and we created a plane, and then if we integrate into the plane, we get I guess you'd call it a block of certain thickness. And actually, this is how they derived the horizontal well solution. They made the block be symmetric, and that would be a horizontal well. But now I want to put fractures along it. How are you going to derive that? This is not a petty 620 question. This is a much more difficult case, isn't it? Can you use a symmetry element? Sort of. Except that you have to know what? You have to know when the pressure distributions bump into each other. Not the tip, but the pressure distribution itself. When does it bump into each other? This is probably one of those things where if you were thinking about it, you'd always do this with a numerical solution rather than with an analytical solution. And most of the early solutions were symmetric, superposition type solutions. As a quick quiz question, what year was the first horizontal well with a multi-fracture model created? Just quick, anybody? It's 1986, 87. Some guys at Shell. Ben Kreistic, really smart guy. Really, really smart guy. Big kid, though, likes to play foosball and pool and everything else. He was a faculty member in Canada and in the Netherlands for a little while, but he's done some really amazing work, really bright guy. They did a finite element solution for this problem. So we actually derived this problem almost 20 years before we started using this in the field. But I don't think anybody in their wildest imagination expected to see 100 stages or 200 stages. How many of you have used the analytical solution in ECRN? Anybody? In the CAPA system? How many, what's the limit of fractures? It was 100. Do you know why? Because the guy who wrote the software thought that nobody would ever have more than 100 fractures. So obviously they had to recast the solution. What about these solutions that you hear about, the so-called trilinear solutions, etc.? These are approximations. You know, Dr. Oscan was telling me it was not his intention to create this hysteria over the trilinear solution. They just came up with something that was a quick answer. And of course, it has to be properly sequenced or superimposed in order to generate a horizontal multi-fracture well solution. And they show in their paper it's not exactly right. But because it's so much faster, people, bang, went to that. Just sort of think about it before you jump on the bandwagon. Okay, so tomorrow night we talk about naturally fractured reservoirs. And what's the difference between naturally fractured